Okay, hello everybody. This is David Careau from the Lighting Institute in Cleveland, Ohio. I am coming to you on this beautiful sunny day. We've got a beautiful blue sky, and it's going to be probably about 70 degrees today. I know that many of you are probably on pins and needles at this point since your test is coming up on November 3rd. And what we're offering here is a 3-video presentation. It's going to be over the next few weeks. The details on the next slide. But what I want to bring up first is this candidate handbook. The candidate handbook is your best friend at this point. It greatly details exactly what's going to be on the test. It breaks it down by subject matter. It talks about the multiple choice. It talks about the 80 application questions, and it also talks about the study material. So please read this candidate handbook cover to cover. The website is there on the bottom, which I'm sure you're all aware of, and make sure you get a good night's sleep the evening before November 3rd so that you're bright and fully awake to sit for this 4-hour exam. So what we're doing here at General Electric is we're providing a series of webinars free. They're going to be 1 hour in duration, starting at noon to 1 o'clock Eastern Standard Time. Today is the first one, Science and Lighting, Basic Electricity. October 12th is the second, and then October 26th will be the third and final. There are CEU credits that are available, so if you need those, let us know. And finally, what we're going to be talking about today, we're considering intermediate to advanced. So hopefully you all have background in the industry. You wouldn't be sitting for the test if you didn't. But what I'm hoping to do is fill in some gaps. Now, this certainly, these webinars do not cover all the material you need to know for your test. This is really a background set of webinars to build a foundation upon which the other study material can be built upon. And that's why we've broken it up into these 3 general categories. So you do want to go back to that candidate handbook and make sure that you do study the material that is recommended. The outcome of today's webinar are really these 4 points. I'm going to be covering the most common electric light sources, just kind of briefly, because really the next webinar is going to dive into them much deeper. I'm going to be talking about some lighting metrics that you probably heard of and you're going to need to know for the test. Spectral power distribution, lumens, candelas, Illuminance, luminance. Color metrics such as color temperature, color rendering, R9, those are also going to be covered today. And then finally, I'm going to touch on Ohm's law. I'm going to touch a little bit on 3-phase power, and we'll do some quick energy calculations so you can figure out how much energy it costs to burn a LED at a certain kilowatt hour, dollars per kilowatt hour cost. The topic of lighting is rather daunting. When we look at just the light sources that are available, there are literally thousands and thousands of different lamps and ballast combinations, and there's literally thousands of different luminaires. Being an LC candidate and sitting for the test means that you need to be familiar in a general way about these different families of light sources. And the easiest way for us to really jump into this and to simplify it is to break it into 3 common categories. So the first category of light sources that have been out there, and they've been out there a long time, is 1879 with Thomas Edison's first practical lamp out of Menlo Park, is the incandescent and halogen lamp. That is simply a hot, I should say it's a hot wire in a bottle. What's used today is a tungsten filament. That filament's inside of a glass envelope. That envelope has some kind of a a gas in it that is stable, such as argon or nitrogen. And that gas isn't easily ionized, and that's why that gas is chosen. So it acts as an insulator. And when you put voltage across the two ends of that tungsten filament with the right current going through it, the thing glows and it incandesces. That is your most basic light source, and they are still out there. What I want you to remember with these is something called lumens per watt, which is the amount of light, lumens, for 1 watt of power. So 17 lumens for 1 watt of power is what you typically get out of an incandescent lamp. The best ones, that would be 100 watt. As the watts go lower, the LPW gets poorer. Now, if you go to halogen, the lumens per watt can go as high as 25 to 30 lumens per watt, but that's still at the low end of what's available commercially today. If we move to the next category, which is called discharge lamps, there is no filament. Instead, there's a glass envelope. In that glass envelope is going to be mercury. So all discharge lamps have mercury in them instead of the filament. When electricity is now put across those two wires that are sticking into that glass envelope, you begin to heat up the mercury. The mercury vapor pressure increases. As it increases, more current is conducted, and it begins to glow. You start melting in a metal halide lamp, for instance, the salts that are in there, and boom, the light finally warms up. So discharge lamps, certainly metal halide and high-pressure sodium and mercury have a warm-up time. Fluorescent lamps, not so much, but T5s can take some time to warm up. So a discharge lamp makes light with a plasma, and that plasma is an electrical arc that is between the two electrodes, and that is basically how those work. Once again, we'll get into it more next session. Lumens per watt on that are as high as 95. And then finally, LEDs, light-emitting diodes. Those use electronics to generate light, where electrons actually move across a junction and fall into the positive side, which has holes. And as the electrons fall into the holes, photons are emitted. And depending on the structure of the LED and the phosphor that's on it, you can get different color temperatures and different lumens per watt levels. You'll notice those lumens per watt vary anywhere from 45 to about 180. So significant improvement on the lumens per watt, or the efficacy, from this latter technology. The other thing I want you to remember is that discharge lamps as well as LEDs require a ballast or a driver, and that's a device that goes between the light source and the voltage source, and it manipulates the line voltage so that the light source can work, and we'll get into more of that in the next seminar. This is just a summary of the light sources that generally are in these three different categories. So a filament lamp, which is, once again, incandescent halogen. Those are the two primary filament lamps. Discharge lamps fall into two categories, low pressure and high pressure. You see the names below in the boxes. We oftentimes use acronyms, LFL for linear fluorescent lamp, CFL, compact fluorescent lamp, LPS, low pressure sodium. Those would be your low pressure lamps, meaning that when they're operating at full output, the pressure inside the glass envelope where the discharges is actually below atmospheric pressure. Discharge lamps that are considered high pressure would be HID, high intensity discharge. They come in three families: metal halide, high pressure sodium, and mercury. Metal halide come in quartz metal halide and ceramic metal halide. Ceramic metal halide being the newer version, much better color consistency and much higher color rendering. High pressure sodium are those yellow street lights that you're going to see driving around the world. And then mercury is an obsolete technology, but I list it there because they're still out there. And then finally, LEDs come in organic LEDs and silicon-based LEDs. The silicon-based LEDs are what's used commercially in commercial light sources. OLEDs you're going to find in your cell phones and your tablets, maybe in your LED TV at home, but OLEDs haven't really broken into general lighting, and those are your semiconductors, and those are the ones that now can be available with delivered 180 lumens per watt at mean lumens and 200 lumens per watt when brand new out of the box. Looking at what comes out of the sun, I'm just taking you back into some basic science here. Roy G. Bibb, red, orange, yellow, green, blue, indigo, violet. Those are the 7 primary colors coming out of the sun. When those wavelengths of light hit the Earth, we have white light. A lot of other electromagnetic radiation is also coming from our sun as well as from our solar system and even outside of our galaxy. And what we're most interested in is the light sources that we can see with our eyes, and those would be the ones in the middle here that I call the visible spectrum. So the visible spectrum goes from about 380 nanometers, that's the wavelength, to about 780 nanometers, and that is your rainbow, your red, orange, yellow, green, blue, indigo, violet. Now, when we look at a light source, we can actually look at it in terms of what wavelengths of light are coming out of it, and we can actually sort that light by the wavelength. And what that allows us to do is generate something called a spectral power distribution graph. So I have a light bulb here. It's putting out light. That light has different wavelengths of energy. Those wavelengths of energy are, in this case, acting as particles of different color, and if I sort those particles by their wavelength, I literally make a graph that looks like this. On the far right is your long wavelength, that is your red. On the far left is your purple, violet, and indigo, and that's your short wavelength. If we sort by long to short wavelength from right to left, this particular light source, which I believe is a compact fluorescent, would have a spectral power distribution that looks like this. If we go to a real spectral power distribution, like the sun, you'll notice that it's not spiky. It's actually very continuous. It does fall off in the deep, deep blues and indigos. It's relatively flat from red to green. The CRI, color rendering index, of the sun is 100 because it renders color so well. So this would be the spectral power distribution of the sun. I have a number of them on here. Depending on the time of day, the spectral power distribution does change. What I've got highlighted in color is the sun and sky, with the sky at 6,000 Kelvin. And we'll talk about Kelvin and CRI in a minute. This is what incandescent spectral power distribution looks like. Notice that the blues and the indigos and the greens are very muted. And what's interesting is both the sun and incandescent halogen have a CRI of 100. We'll talk more about that in a minute. But this is a situation of what colors are present in the spectrum of this light source. The reason that spectral power distribution is important is it tells you how colors will be rendered, and therefore if you, for instance, are working with, let's say you're sorting black laundry and blue laundry and purple laundry, you wouldn't want this light source as an illuminant, because the blacks, the purples, and the blues would all look the same, because there's no wavelengths of light at those particular colors to actually activate the colors in whatever you're sorting. However, if you're sorting items that are various colors of red and orange and yellow, you are going to be able to tell very, very easily and be able to differentiate very fine color differences by using a light source like this. This is what an LED spectral distribution looks like. Notice the big spike with the blue LED. Phosphorus put on the LED, that's what adds in the green and the red. We get red, green, blue, RGB, and humans see white. Depending on the ratio of RGB, red, green, blue light in the spectral power distribution, that's going to tell you what color temperature you're going to have and how well the CRI, I should say how good the CRI number is going to be. Here's a bunch of spectral power distribution curves for a number of different products, and you'll notice that the ones that are white have a lot of RGB, red, green, blue, or at least enough so that we can differentiate them as a white light source. The two on the lower left are yellow because there's not enough red, green, blue, RGB to actually make them appear white to us. The two lower right, two lower left, low pressure sodium and high pressure sodium, those are going to be seen as yellow light sources because they do not have enough red and green to cause us to see them as white. I'm going to jump into color temperature now. Color temperature is an indication of the color of a white wall. So if you have a warm color temperature around 3,000 Kelvin, it's going to light up a white wall with kind of a yellow, orange, red hue. It's still going to be white, but it's going to be more toward the red. If you have a color temperature source that's cool, let's say 4,100 Kelvin, and you illuminate a white wall, it's going to look more blue-white. This is a continuous spectrum. And as we look at this, let me show you where this came from. So Kelvin is the unit that correlated color temperature is measured in. And if you think of this cup of water here, which has 3 thermometers in it, one thermometer is Fahrenheit, one thermometer is a Celsius thermometer, and the third one is a Kelvin thermometer. Now, as this water is cooled down and ice is just beginning to form, you would read the numbers on these thermometers as follows. 32 Fahrenheit for the water with the right thermometer. The center thermometer is going to measure the temperature of that water at 0 degrees Celsius, and the one on the left is going to measure the water at 273 Kelvin. Those are all the same temperature, just in different units. The water is what the water is, and whether you think in terms of Celsius, Fahrenheit, or Kelvin, all we're talking about with Kelvin is a different scale for measuring temperature. Let me take it to the next level. If I have a horseshoe, a piece of iron, and I heat it up to the point where it turns orange, I take a Kelvin thermometer and I touch it to that orange horseshoe, it's going to measure around 2200 Kelvin. If I add in another torch and make this even hotter, and I make the horseshoe glow yellow, I grab a Kelvin thermometer and I measure the temperature. My heavens, it's up to 2700 Kelvin. It's gone up 500 Kelvin, and it's actually changed color because of that 500 Kelvin increase in temperature. Finally, if I grab every torch I own, all 3 of them, and I heat the horseshoe up to white hot, I grab my thermometer, it's now going to measure 4100 Kelvin, considerably higher than the orange or the yellow. So what I want you to understand is what this word correlated color temperature means. When we say correlated color temperature, what we really mean is that this horseshoe that's at 2700 Kelvin, which I measure with a thermometer, is going to glow a certain orange color. Turns out that a high-pressure sodium lamp, when it's running, it glows at the same color. So what we're doing is we're correlating the color of a black body, which in this case is being simulated by a horseshoe, to the color of our light source. And when the correlation is very good, we then assign that color temperature to that light source. So the high-pressure sodium lamp is 2200 Kelvin because it's correlated back to a 2200 Kelvin black body, or our simulated black body, which is this horseshoe. Likewise, an incandescent lamp matches the color of a black body at 2700 Kelvin, and therefore an incandescent lamp is 2700 Kelvin color. Finally, if you grab a linear fluorescent lamp that says SP41, that 4100 Kelvin on that lamp is correlated back to the black body, which is at a temperature of 4100 Kelvin and emitting that color of light. So, thing to take away is when we talk about color temperature, it always goes back to the black body, and it's a correlation between this known color and whatever we're comparing it to. In this case, these 3 different light sources. The other thing I want you to know with color temperature is that as CCT increases, Kelvin increases. So as the temperature goes up, so do the Kelvin temperature. That makes sense. What doesn't make sense is that as the temperature goes up, the colors are actually called cooler. So a higher temperature is actually a cooler color. A warmer temperature is actually going to be a hotter color. I should say a cooler color, okay? So cooler colors as the temperature goes up, warmer temperatures as the colors go down. So actually a color temperature that is cooler, 2200 Kelvin, is actually called a warm color temperature, and a 4100 Kelvin, which is hotter, is actually called a cool color temperature. You just need to memorize that. It may not make sense logically, and it certainly doesn't, but that's the way it's been done for at least 70 years. Here's just a quick chart showing you color temperature in Kelvin and different light sources. So a light source that's called a daylight light source, like an LED, 5500 Kelvin. Cool white, around 4200. Notice that the blues are getting a little bit more whiter, around 4000 Kelvin. That's a blue-white. You get into the 3000, 2700 Kelvin light sources, and now they're going to be more yellow-orange. Last thing I want to state is we never use the word degree with Kelvin. You talk about degrees Fahrenheit and degrees Celsius. When you talk about Kelvin, which is an absolute temperature scale, there are no degrees. So we talk about 8,000 Kelvin, 5,000 Kelvin. Never say 5,000 degrees Kelvin. That makes no sense because Kelvin is an absolute scale, and there are no degrees in the Kelvin scale. Okay, so just remember that. How do I choose CCT? Real simple. Here's some takeaways, and once again, y'all have these slides, so when you see these slides, please feel free to make notes on them, but don't worry if I'm going too fast, or you can read these slides later. 2,500, 3,000 Kelvin is general residential lighting, hotels, restaurants. Typically, it's where people go to relax or at home. 2,900 to 4,500 is going to be more general lighting in commercial spaces like schools and industry and offices and medical facilities. 5,000, 7,500 Kelvin, more specialty lighting, not so much for general lighting, although people can put high color temperature in their homes if they like, or in their offices or schools. Let's move to color rendering. So color temperature only tells you what shade of white a wall will be. It will tell you nothing about how colors look. Color rendering, which goes from a scale from 0 to 100, 0 the worst, 100 the best, will tell you in a relative way how true the colors are. So a 75 CRI is going to give you truer colors than a CRI of 22 versus a CRI of 0. Now, CRI is measured with 8 color chips, R1 through R8. The process is outlined in the 1, 2, 3 steps on the upper left. The upper 8 chips are lit by the control, which is either the sun or an incandescent or halogen. Those colors are recorded. The lower set of 8 chips is recorded by your test lamp, in this case an LED. The differences on the observed colors, so how much the colors differ between the control and the test lamp. So R1 looks this way with the control, looks this way with the test lamp. How much does it differ? A number's assigned to that. Those are all added up, divided by 8, and that's how the color rendering is defined. You need to know that color rendering is only done when sources have similar CCTs. So if we're going to be going with a high color temperature LED, we're going to use the sun. If we're going to be going with a low color temperature, 2,700, 3,000 Kelvin LED, we're going to use a halogen or incandescent lamp as the control. Okay, so always match your CCTs with your controls and your test lamps. The 8 colors look like this. These are the names that are assigned, R1 through R8. There are additional colors that were defined by the CIE when this standard was developed, R9 through R14. What I want you to know is about R9, which is something that's touted very much in the LED industry, and that is a strong red, meaning that there's a lot of red in that spectral power distribution, and therefore red's going to be highlighted in anything that's illuminated by that light source, like an apple or a tomato or the red tie or the red purse that a lady may be carrying. So a high R9 means that there's a lot of red in the spectral power distribution, and that means that the red's going to look better either in the material or the red that's in our skin tone. Here's a general rule for different light sources and CRI. Typically for indoors, you want to have a CRI of 80 or above. Today for retail, we typically want 90 or above, and the CRI for LEDs outdoors has centered around about 90 CRI, so that's been deemed good enough for outdoors. Let me get into some basic lighting terms here. So we talk about a candela, and a candela is defined as the light coming from a single candle. It's emitted omnidirectionally in all directions. So a standard candle emits 1 candela in every direction. As we move through this, if we move 1 foot away from that standard candle and draw a circle, as you're seeing here in the graphic, what I've just defined now is 1 foot candle. So if you go 1 foot away in any direction from the standard candle, that's defined as 1 foot candle. Now if we make that circle into a 1 foot radius sphere, so now it's a 1 foot sphere or a 2 foot diameter sphere, and we cut a 1 foot hole out of the side of that sphere, doesn't matter what the shape of the 1 foot hole, 1 square foot hole is, so 1 foot by 1 foot, that amount of luminous flux coming out of that 1 foot square hole on the side of that ball is defined as 1 lumen. Okay? And then finally, if we, in the metric world, if we make, instead of 1 foot away, we go 1 meter away, which is approximately 3 feet from the standard candle. We draw a 1 meter radius circle. Every point along that line is going to be measured in lux as opposed to foot candle. And this is how we define illumination or illuminance in the metric world. So 1 meter away from a standard candle is 1 lux everywhere along that surface. 1 foot away from that standard candle everywhere along that surface is defined as 1 foot candle. Okay, so foot candles are a unit used in English-speaking, or I should say English countries, which would be Australia, England, United States, Canada, is where you're going to run into foot candles. You're going to run into lux and metric countries. So everywhere in Europe, South America, Africa, Asia, most likely it's all going to be lux, unless it was a former British colony. Likewise, if you have a 1 meter radius sphere around this Candela source, and you cut out a 1 square meter hole, the amount of luminous flux leaving that 1 square meter hole is going to be defined as a lumen. So a lumen in the metric system is the same as a lumen in the English system. Last thing you need to know is the relationship between a foot candle measured in lux and a foot candle and a lux measurement, which are both units of illuminance. 1 foot candle equals 10.76 lux. That could be on your test. You want to know that, okay? So 1 foot candle is about 10 lux. So if you have a 100 lux source, that's about a 10-foot candle surface, okay? Foot candles are the amount of light on a surface. It has nothing to do with the surface material or the reflectance of the surface. It's just simply the amount of light hitting a surface, and that can be measured both vertically and horizontally. If we want to measure the amount of foot candles on a desktop, for instance, indoors, foot candles are measured 30 inches off the ground. You want to know that. That's a national standard. If I put a bunch of fixtures up in my ceiling, each one of those fixtures is putting out an amount of lumens. I can add up the total amount of lumens from those 8 fixtures. I then want to divide it by the length and the width of the room. So the equation looks like this. Foot candles equals total lumens divided by the length times the width, or the surface area of the floor. That's going to give you your average foot candles on the floor. Okay? If you multiply it by 0.5, it's going to give you your average mean foot candles. Okay? So that's what the 0.5 does. It puts in your losses due to aging and due to the shape of the room and the reflectances of the room. That's what CU and LLF are. And what I want you to take away from is, if you do need to do this in real life, you can do it by the way I just did it, either for initial lumens, don't use the 0.5 in the equation, or for average mean lumens, you want to put the 0.5, and that's a rough estimate. You can also use a foot candle meter and walk around the room with the meter sensor 30 inches off the ground, take a bunch of measurements, add them up, divide by the total, and get the average. Also, I just want to make sure you all are clear that the actual formula for foot candles is this. Average foot candles mean, meaning at the 50% life point on LEDs or 40% life point on fluorescent or HID or a halogen. So the mean average foot candles in a space is you take your initial lumens, which is your 100-hour catalog lumens, multiply it by your coefficient of utilization, which has to do with the shape of the room and the reflectances of the room and the optical characteristics of the fixture. Light loss factors, which take into effect dirt depreciation and lumen maintenance, divide that product by the area of the work plane, which in this case would be our length times our width of the room, and that is actually the equation that you might have to plug some numbers into for your LC exam. Now, foot candles are specified by a number of organizations. The National Fire Protection Association, NFPA, has a chapter in their handbook, Life Safety Code handbook, that specifies foot candle levels for emergency egress and emergency lighting. OSHA also specifies foot candle levels, and those are codes. So NFPA and OSHA foot candle levels must be hit in new construction and major renovation. The IES, the Illuminating Engineering Society, and the IDA, International Dark Sky Association, they also publish foot candle targets, and those are going to be measured based on their recommendations. Those are not codes. So this slide, what I want you to take away is that NFPA and OSHA are code. You must hit those. Recommended foot candle levels are nice to hit, but you don't have to unless they're written into code, and those are going to be gotten from the Illuminating Engineering Society's Lighting Handbook or documents from the IES and the IDA, for instance, like the MLO, the Model Lighting Ordinance. Here's some typical foot candle light levels that we have taken out of some old IES documents. You really need to go to the IES handbook that came out in 2012 to get the most current. So for instance, for a general office, 50-foot candles. For a conference room, 30-foot candles horizontal, 10-foot candles vertical. Notice there's a huge range in here. So these are the kind of targets that we typically shoot for when we're doing a lighting layout, but once again, you want to reference the IES handbook. It has 17 chapters, 524 pages of required lux levels. And once again, take those numbers, divide them by approximately 10, and you'll get your foot candle levels. We're now moving on to Candela plots. Candela plots are something that you need to know about because this is actually how the light is actually distributed out of the light bulb or out of the fixture. And you'll notice that there's a red and blue curve here. The red curve and the blue curve are 90 degrees apart. In reality, they're just plotted on a plane on these particular graphs. So in the case of the lower left, the blue and the red are coincident. The two curves fall on top of each other. So you can kind of assume that that light fixture has a uniform light output. The light is uniform regardless of whether you're looking, let's say, north, south, or east, west once it's mounted in the ceiling. These other ones have slight differences, north, south, east, west, once again, once it's mounted. And the lower right, huge difference between the beam spreads in one direction versus 90 degrees apart. Now, these plots come from something that's called a fixture photometer or a goniometer. And the fixture photometer, as you see here, our friend Bob is actually holding the mirror. This mirror is actually on a motor. It's at an angle. It will actually rotate 365 degrees around that light source. And every degree or so, it actually records the amount of candelas coming out at that angle. So when we talk about candelas, it's the amount of light coming out of the light source at a particular angle, and it's recorded on those graphs that I just showed you. And from those graphs, you can actually pick off the candelas at a particular angle. In the world today, we do define our candelas by two different angles, and you'll see something called a beam angle and a field angle. So what you need to know with these two terms is a beam angle is the amount of light in the beam spread that goes plus or minus 50% from the center. So if you take your light coming out the middle, which would be 100% on the graph if you go to the bottom, and you go to a 50% reduction to the right or a 50% reduction to the left, those are the blue, I should say the green triangle I have drawn there, just happens to be 45 degrees. It could be anything based on the bulb. The light within that plus or minus 50 degree beam is called your beam angle. And that's important when you're doing a lighting layout to know what the beam angle is. Now, the field angle goes much wider. It's the light output from your light source all the way up to, from where it's the brightest, all the way to where it drops to 10% of its maximum. So if you go plus or minus 10% of your maximum, that angle, whatever it's measured at, is called your field angle. So field angle is where your center beam candle power drops to 10% of its max, and beam angle is where your center beam candle power drops to 50% of its max. This might be on your test, so you need to know about that. So let me walk you a little bit more through these candle power curves. So I have my light source. I put in this polar graph here, 0 degrees, 15, 30, 45, 60, and 90 degrees. I measure with my goniometer, and I find out that the graph actually looks like this. Okay, so this is literally what the Candela graph looks like. Now, off of this graph, I can actually get some numbers, right? So if I go to this point right here, which is 0 degrees, it's basically called nadir, 0 degrees, which is straight down out of the bulb. From this graph, I can literally take that little red point that's intersecting that black line, and I can read about 1,900 candelas at 0 degrees. I can also pick off other points. For instance, I can go to this maximum amount of light. So the maximum amount of light out of this particular light bulb is about 2,200 candelas at 20 degrees. So the maximum light is not right in the center of the beam. It's actually 20 degrees off of center. That's kind of interesting. So what I want to do now is move to some calculations that hopefully can help you understand what is going on with these next few slides. So let me walk you through these. So this next slide, which I just pulled up, let me just move to that slide. Okay, this slide, which we're all looking at. Let me do an example for you. My candelas are given to me as 1,900, as you just saw on the last slide. My distance from the bottom of the light source to the floor is 10 feet. So that I'm calling D. So my candelas or luminous intensity is 1,900 candelas at nadir, 0 degrees, and I can calculate using this equation. Foot candles at nadir equals 1,900 divided by 10 squared, which is 100. 1,900 divided by 100 equals 100. So I know that my foot candles for this particular light source directly out of the source at 0 degrees or nadir is 19 foot candles. Okay? Notice I have cosine of 0 degrees, and cosine of 0 degrees is 1. So it doesn't impact the calculation. Now what happens if I want to find out what the light source is, let's say on the wall next to the light source. So down on the floor, we know that it's 1,900 candelas and it's 19 foot candles. Well, let's look at that big gray thing in the middle here. I have a circle of light in orange drawn there. And the way that you calculate the foot candles on the wall is what I have on the right. So the first thing you do is you go to the point on the wall where you want to measure the light, and you draw a line perpendicular to the surface. So this is a vertical surface. I draw a line out that's horizontal. That's perpendicular to the surface. I then go back to the center point, which is where I want to measure, and I draw a line back to my light source. That is the angle that I want to measure for this calculation. So in this case, I want to put in, I measured it 50 degrees. I know it's 1,000 candelas because I got it off that other graph. I just kind of made that up for this calculation. I'm telling you that I'm 15 feet away. That's the length of the distance from the source to the center of that ellipse on the wall. I plug into my equation 1,000 times cosine 50 divided by 15 feet squared, which is 225 feet, and I do that calculation. I come out with 2.3 foot candles on the wall. So the thought here is, if you are asked to calculate the foot candles on a surface, if it's a horizontal surface, directly underneath the light source, you draw a line perpendicular from the surface. You calculate the angle between the surface and the light source. For our 1,900 candelas and 19 foot candles, that angle is 0. So therefore, we have the calculation on the left, calculation on the right. We draw any point on this wall. They tell you it's 50 degrees. They tell you what the candelas are, and they tell you what the angle is. You plug it into your equation, and boom, you've got the answer. You just got some points on your test. So go through this and understand it, and you will benefit from doing that. I'm going to jump into electricity now for the next 15 minutes. So if we talk about basic electricity, let's talk about volts and amps. For those of you who think about a water pipe, the pressure in the pipe is similar to the volts that are inside of a wire. So the electromagnetic force, or the pressure of the electrons inside the wire, has an analogy to the pressure that the water has inside of the pipe. Now, depending on how much you open or close that valve, that's what's going to tell you the rate at which that pressure is allowed to flow. So you can have a huge amount of pressure, but if you don't open that valve, nothing's going to flow. If you open that valve all the way, you're going to have a lot of flow. So the current in a circuit is the rate of flow of electrons, and the voltage is the pressure that those electrons are pushing. Volts times amps, V times A equals power. That's an important equation to know, and that's true for DC circuits, okay? So volts times amps equals power. Power is measured in watts, okay? Watts is a unit of energy. So watts, as I just said, is volts times amps. Energy is actually measured in watts times time, okay? So in order to actually calculate the amount of energy that's being used, you actually have to take the kilowatts times the time to get watts times time. So when we talk about energy, the units we typically use is a unit of wattage times time, and in this case, we're talking about kilowatts times hours. It could be watts times seconds, but in the industry, we buy electricity based on kilowatts times hours. And it usually is written as dollars per kilowatts times hours. And what's typical average in the United States, about 11 or 12 cents, is what it costs per kilowatt hour of energy. Let's do a quick calculation here. How much does it cost to operate a 60-watt incandescent light bulb 12 hours a day, 365 days a year at 10 cents a kilowatt hour? So this is the equation. It's real simple. You put in your amount, the cost of your electricity, 10 cents per kilowatt hour, times your kilowatt power. This is a 60-watt light bulb, so it is 0.06 kilowatts. Okay, hopefully you see that. Okay. I'm telling you they're burning them 12 hours a day, and I'm telling you they're burning them 365 days a year. If you do that calculation and you cancel out your terms, what you're left with is dollars per year. You do the math, and you find out it costs you $26.28 to burn this light bulb given those conditions. Let's put in an LED, a 9-watt LED. Gives you the same amount of light. Do the same calculation, but put in, instead of 0.06 kilowatts, it's now 0.009 kilowatts. Everything else is the same. You've dropped from $26 a year down to $4 a year. This is why LEDs are so important. Same amount of light and significantly less than a quarter the amount of energy. When we talk about AC and DC, the beginnings of DC were really with Thomas Edison and J.P. Morgan funding him. Edison came up with the first alkaline battery. That's to be compared to Nikola Tesla. His name got thrown off. So anyway, this Nikola Tesla on the right and George Westinghouse on the right, and they were the AC guys. So we today are doing AC and DC every day. Typically, all of our light sources other than LEDs run on AC, alternating current. LEDs run on DC. So let's look at what DC is. If you grab a battery and you put it on and you plot the voltage over time, you would see that you have a constant voltage, in this case 0.7 volts DC from this battery, okay? And it doesn't change over time. It's just a constant voltage. Now, if you do that same thing with an AC light source, I should say an AC power source, what you'd find is to get the equivalent amount of heating in a resistor, you would actually have to have a voltage, AC voltage, that looks like the one on the right. Okay? Notice that it starts at 0, it goes up to 1 volt, goes back to 0 at 3 seconds, drops down to full voltage again, a -1 volt at 5 seconds, and so on and so on. So this oscillating voltage literally turns on at 0, peaks out at 2 seconds, drops to 0 at 3 seconds, reverses direction, peaks out at a -1 volt at 5 volts, and so on and so on. In order to get equivalent heating between a 0.7 volt DC source and an AC source, we've come up with this term called voltage RMS. And voltage RMS, to get the same amount of heating in a resistor, is you'd have to have an RMS voltage that has a peak when divided by the square root of 2, 1.414, that would equal the same amount. So in this case, a 1 volt peak sine wave is going to give the same amount of heating in a resistor as a 0.7 volt DC battery. Volts RMS is an important thing to know. Anytime you need to know the volts RMS, just simply find the peak of your AC waveform, divide that by the square root of 2, and that will give you the AC RMS voltage. Why do we use AC? Well, here's 3 of the reasons. Ohm's law is important, so you want to know this. Now, this is, once again, you're going to have this, but all you really need to know are the ones I have in red. If you know P equals I times V and V equals I times R, so power equals current, I is current, times V voltage, or voltage equals I current times R resistance. So these 2 equations on the upper left, you can derive every other equation in this table. Let me show you how you do that. So if you have voltage equals I times R, substitute the current for the equivalent power divided by voltage. If you simplify that equation, you get power times R divided by V equals V. Simplify it again, take the V in the denominator, throw it on the other side of the equal sign. V squared equals power times R, or V equals the square root of power times resistance. Every equation that we have here you can develop from V equals I times R, or power equals I times A. I should say I times V. And therefore, if you do run into a problem on the test, you can always come up with the one you don't know. Okay, so there's a few other derivations there on the left. In summary, when we talk about the RMS voltage, we take the peak times root 2, and that gives you AC voltage RMS. There's something called the period, and the period is the amount of time for a complete positive and negative cycle of an oscillating sine wave. The period is defined as 1 over the frequency. So for a 60 hertz sine wave coming out of the wall, which would come from your utility, 1 over 60 says that this positive cycle and negative cycle happen in 16.7 milliseconds. The other thing I want to introduce here is, remember I said that power equals volts times amps, or volts times I, which is current. That's true for a DC source. Power AC actually has another term that's created, and that's power factor. So let's talk about power factor. So power AC is voltage times current times PF, power factor. Power factor is defined as the phase angle between the voltage and current. So the curves on the left, the voltage and current both start at the same time, time 0. They are in phase, so the power factor is 1. If you go to the one on the right, you'll notice that the power factor is not 1 because the current actually is starting 60 degrees after, or is actually leading the voltage by 60 degrees. It may come up on your test, these 2 statements on the right. For a capacitive circuit, the current leads the voltage. In an inductive circuit, the voltage leads the current. You need to just memorize those. You also could say for a capacitive circuit that the voltage lags the current. Likewise, for the inductive circuit, you can say that the current lags the voltage. And I just noticed that C in the lower right, that should be an I, okay? So voltage leads the current for an inductive circuit, or current lags the voltage. It's the same thing, just saying it in a different way. So here's your power factors. So if you have 0 degrees between your voltage and current, your power factor is 1. I'm sorry, your degrees are 1, so cosine of 0 degrees is 1. So you're back to the DC instance where voltage and current are always in phase. As your phase angle changes, you'll notice that your power is going to also change. So your real power is going to be now adjusted by your cosine theta. Let's talk about transformers. Transformers are not real scary things. They're actually kind of simple. What you need to know is the law on the bottom, that power in equals power out. On an ideal transformer, the amount of power you put in equals the amount of power you take out, and there's going to be potentially a ratio between the windings on the power in versus the power out. The ratio of those windings tells you whether that transformer is going to step up the voltage, which means more winding on the output than on the input, or is going to step down, meaning fewer turns on the output than the input. The little example I have in the lower right, power in equals power out. So if I have 12 volts RMS going in and 10 amps going into the input, that means I'm going to have 120 volts RMS on the output and 1 amp on the output. Notice that 12 times 10 on the input equals 120 times 1. If you get that question, all you need to remember is power in equals power out. Power factor does not come into play because it cancels out because it's the same core. Power factor is the same on both sides. Okay, so that's a simple one to get a correct answer on. Let's talk about three-phase power. Now, three-phase power means that we now have our voltage and our current from three different sources starting 120 degrees apart. So phase 1 starts at time 0, phase 2 starts 120 degrees in the future, and phase 3 starts 240 degrees in the future. So we have phase 1, phase 2, and phase 3. That's actually made by three different supplies, as I have shown here in this Y circuit. So this is a Y three-phase circuit. Each one of these voltage supplies is creating voltage 120 degrees out of phase with the others, as I showed on the prior slide. If you take a voltage meter and you measure on this 480 volt three-phase circuit, phase A to phase B, you'll measure 480 volts. Phase B, from phase to phase, you get your full voltage. So phase A to phase B, phase A to phase C, or phase B to phase C, you'll get your full 480 volts output. What you need to know is that if you go from phase to neutral or phase to ground, you need to know this equation. So phase to phase is going to be full voltage. Your phase to neutral or phase to ground is going to be your full voltage times root 3, square root of 3. So phase to neutral is, for example, if you have a 480 volt line and you want to know what your phase to neutral is, you take 480 volts divided by the square root of 3, and that would give you 277 volts. You'll oftentimes find in commercial applications that there's 277 volts and 480 volts in the factory, in the parking lot, along the roadways. The way that's happening is exactly this way. They have a three-phase system, and in some cases they pull the neutral, and now they can take the phase from either phase A, B, or C and connect it, either one of those, to the neutral, and they'll get 277 volts. If they pull two of the phases to the pole, they'll have phase to phase, which would be 480. They now have a choice as to what they want to do. There's other very common voltages that are done in three-phase circuits. Like a 208 three-phase circuit is how you get 120 volts off a three-phase system. There's also a system in addition to the Y that's called a delta. And instead of the three voltage supplies being connected in a Y, they're actually shown here in a delta loop. Notice that there's no intrinsic ground, so you got to pull a separate ground wire. Once again, phase to phase is going to be the full voltage. Phase to neutral, simply take the full voltage times root 3, and you will get the proper phase to neutral. So as you begin to look at this, you start understanding why there are common industrial three-phase voltages. So in Canada, they've got 120 and 208. Once again, take 208 divided by root 3, you get 120. They have 480 and they have 240 volt dedicated. They have 480 volt dedicated. And then they have three-phase 347 and 600 volt, because 600 divided by root 3 is 347. Likewise, in the U.S., we've got 120 and 208. That's a three-phase, very common. 277 volt, 480 volt three-phase. We also have 480 volt single-phase. We also have 120 volt single-phase. So here's your equations to see why three-phase is so popular and why do we have these typical voltages. This is why. Three-phase, why do we use it? Well, here's some of the advantages that Tesla came up with, and we are still enjoying those inventions from Nikola Tesla today. So that is the end of the seminar. I just want to remind you that there's another seminar coming up on October 12th, and that's going to be from noon to 1 o'clock Eastern Standard Time. We're going to do a deep dive into legacy technology. Also, we're going to compare that to the LED alternatives. Finally, on October 26th, we're going to have our third webinar, and that's going to be from noon, once again, to 1 o'clock Eastern Standard Time. And that one's going to be a deep dive into LEDs, dimming, UL type A, B, and C, and then life ratings. So with that, let me turn it over to questions. We've got about 4 minutes for questions. And I ask you to type those into the chat box. And as the questions come, I'll do my best to answer them. So you got about 4 minutes to do that. These slides will be made available to you. Also, this video will be, I should say this webinar will be made available to you with my talking on each slide, which hopefully adds some insights to these different topics. Any questions, guys? Any questions? Let me give you my phone number if you want to call me, 216-266-5508. I repeat, 216-266-5508. If you have a question, give me a call. Hopefully I can answer the question. Okay, Brittany, I'm not seeing any questions. Are you seeing any on your side?
No questions. I'll go ahead and end the webcast.
Okay, guys. Hey, thank you so much for your time. We'll see you at the next webcast. Is this an open book test? Absolutely not. No. No, you're barely allowed to bring a calculator. So you got to bring a calculator that has no memories, no alphanumerics. You're allowed to bring a simple calculator that you can't plug in. You got to turn your cell phones in before you're even allowed to take a seat. It is absolutely not open book. And you want to go to that candidate handbook. It'll tell you all the pluses and minuses and the where and wherewithals for the test. And it is absolutely not open book. It's 4 hours, and they're going to be hard-pressed to even give you a break to go use the restroom because they don't want people talking in the hallway. So usually it's one person in, one person out, and you're losing time when you go to the restroom. So read the candidate handbook. All the information's in there. Any other final questions, guys? It looks like we got about a few more minutes here. I guess, Brittany, let's just hold on until we hit 1 o'clock in case anybody else has any questions. So we're going to leave the line open here. I've got 12:57 on my phone, so we've got maybe 2.5 minutes here for questions. And once again, if you do have a question that I didn't answer during the seminar or something I didn't cover clearly, give me a call, and I am more than happy to talk to you. The goal of this is real simple. You want to pass the test. And I believe passing score is around 70%, 72, 73, somewhere in there. So you do not need to get 100%, but I got to say every single question matters. And you want to give everyone some thought. The multiple choice ones you typically can get through pretty quickly. The application question is going to be a little bit more challenging. They're multiple part. The answers build on themselves. So if you make a wrong answer, that's going to probably direct you down the rabbit hole where you're going to get a lot of wrong answers. So there are some test questions in the handbook, and I recommend you do those as well. So any final questions, guys? Like I said, that candidate handbook, it's a PDF file. Please download it and read it end to end. You had to fill out the application form in it, so I'm guessing you've already seen it. You had to send in your money for the test by September 20th. So if you haven't already registered, you can't take the test this year. You'll have to take it in 2019. So hopefully everybody on the call has already registered and sent their money. I believe the drop dead date for registration was September 20th. The LC credential lasts for 3 years. You do need to do continuing education units during those 3 years so that when you re-up, you send in those CEUs, and then they will look at them, and then they will send you they'll send you along with your approval a new certificate. Also, it takes some money to do that. Are these slides available online? Yeah, they should be on. They should be. Brittany, how do they get to the slides?
So we will be sending this recording on demand following this presentation. And then I believe that you are going to post them on Learning Central as well?
Yes, we will. Yes, we will. So gelearningcentral.com as well as what Brittany just said. So I think we've addressed the 3 questions that are up here. So guys, I'm going to wind it down now. I've got 12:59 and a number of seconds here, so I think we're going to hit the 1 o'clock hour. Once again, study, study, study. You've got a couple weeks. You actually have more than a couple weeks. Look at the candidate handbook. Get your hands on a lighting handbook. I think that's the #1 testing item. And once again, this will be posted, and you can go back and look at what I've given you today. All the best. Keep studying, and I'll see you in a couple weeks for the next webinar. Bye-bye from General Electric in Cleveland, Ohio. This is David Carreau signing off. Brittany, thank you, and we'll do this again. Bye-bye.